tell you what an honor it is to be here. I've sat in the audience at this venue and seen all sorts of famous names come up there, and it's very humbling to sort of be here. It's also very impressive that so many of you are here at 8:30 a.m. on the fourth day of a keynote. This must be a killer conference. I need to make sure I start coming to this. I wanted to, you probably have no idea who I am, and even the font on the website apparently is illegible, so let's take a second just to tell you who I am. I've been in software for just a little over 20 years, and the first decade was pure software engineer. I first started out working for the university building weird tools for a psychology professor. But then I made my way out to the Bay Area at a startup not far down the road called Scriptix, which was a company that was building tools for the Tickle programming language, if you remember that. And it's interesting, Gerald and I were just chatting right before I got here. The company he was working for, Case, had kind of the same relationship to Wireshark as Scriptix had to Tickle, which is, it's an open source platform. We can sort of see a sliver of commercial opportunity. Can we start building tools for it? In typical Bay Area fashion, I'd been in the Bay Area for all of 6 weeks when I was told, actually, we all need to come down. This is all hands right now. Scriptix is over, guys. It's finished. We're getting acquired by a company called Interwoven. Please report to the office every day for the next 6 weeks, although there's nothing for you to do. We'll be giving you a new email address, and we'll figure out what your jobs are soon. And I just kept looking around the room going, is this normal? Is this what happens in Silicon Valley? And Interwoven was a lot of fun. It was one of the big .com darlings of the day, and it was fun, but it wasn't engineering fun. Like, it was great to see a product that was getting great adoption. And John Osterhout and John Graham Cumming, people who founded Scriptix and who were leading Scriptix, said, we've got a great idea. Why don't we start a company specifically focused on software builds? The build at Interwoven was a nightmare. It ran for 7 hours. It was a complete coin toss whether it would work or not. Like, why don't we come up with a tool that makes builds faster? And that company was called Electric Cloud. And now my role starts to change. I start off at Electric Cloud as a software engineer, but I quickly wind up in sort of a sales engineering role, helping us figure out, does this thing actually work in the field? And from there, I was tapped to be the head of product, and I spent some time in solutions and services. And if you do this racket enough, you start to think that, wow, everyone's doing everything wrong. You know what the world needs is a new CEO. I should be the boss. I should start my own company. And that's what I did. I started a company called Selligy with some ex-Electric Cloud colleagues. And Selligy was right around the time the iPad came out, right around the time people were seriously looking you in the eye and saying things like, PCs are going away, it's all going to be mobile. And our vision was to create a mobile Salesforce, or a mobile interface to Salesforce, since I've now spent time in CRM. And that was a lot of fun. For 4 years, I was a founder and built apps and went around and raised funding and all that great stuff. And eventually, we ran out of steam, and we were acquired by a very big company called Veeva. And Veeva was great. They let our whole team stay together and work on some internal projects. And around this time, I get a phone call from my old boss, the CTO of Cloudflare, who I've been in touch with all these years, and says, you've got to come to Cloudflare. We're doing some amazing things, and why don't you come and be part of the engineering team? And so that's my role now. So I sort of had 2 or 3 different major chapters to my career. And it's interesting, my relationship to Ethereal, to Wireshark, I was telling Daryl, I still say Ethereal. In fact, when I type command space, I still type ETH backspace WI. But I was introduced to Ethereal back in 2002 because that first product we were building was a distributed build system. And it was really interesting. It had some properties of, I'm going to send you a command like a GCC compile to run on a remote computer, but it was also a file system. So when that compile was running, it would actually request the source files, the header files, and the .c files from the make system because it could track dependencies that way, which meant that this had all the properties of remote execution and a file system. So we developed our own protocol to make it high performant. And that protocol was based in TCP, and I was on the Emacs side, and my buddy who sat right across from me was on the agent side. We were constantly testing, and neither of us ever wanted to admit that we were wrong. So we were constantly saying, it's your fault. You messed up. You didn't listen. You dropped that packet. You dropped that response. And so my first exposure to Ethereal was sort of this all-knowing referee. Like, all right, that's it. Enough packet trace. Pull it up in Ethereal. Let's see who's right. And that was sort of the way I thought of ethereal for a long time was, it's the Godfather, it's the judge and jury, it's truth. When everything, all else fails, fire up ethereal, and that will answer your question. And we thought for a while about building a dissector, about a way to show our protocol in it, and we eventually actually instead wound up building a little gadget we called the double agent, which was basically a man-in-the-middle proxy, and it looked like an agent to the server and a server to the agent. And that was the first time I had this observation of what I called Liberty Scaffold moment. This is a picture of the Statue of Liberty in 1984. It underwent great renovations. I happened to be in New York. I was a kid at the time. And everyone was looking at the Statue of Liberty going, oh, it sucks. We can't see the Statue of Liberty. And I was like, yeah, but look at that scaffolding. Like, that is really impressive. Look at the engineering behind the scaffolding. And I've realized this happens a lot in engineering across disciplines. When you sort of wake up and discover the infrastructure that you've built is almost more sophisticated or eclipsing the sophistication of the thing you're building. And I started to pay attention to this as an inflection point, especially in software companies. When you discover that your build system and your framework and your infrastructure around it is now more complicated than the widget you're actually producing, that's a sign that you are either about to enter a world of awesomeness or horrible misery. Because the awesomeness is, I mean, you can imagine, the guys who built that scaffold, I've never met them, I'm not a civil engineer, I don't know squat about what's in those bars. But I bet they could probably turn out another scaffold like that if they needed to. And if they needed to do it for 100 Statue of Liberties, they probably could do it. That's a place where there's an opportunity for scale. Anyway, I just thought I'd mention that, since that sort of, these thoughts all came back to me when I was sort of replaying the era of the double agent for me. But chapter 2, once I left core development and I was more in SC and then a director of support and sales and then starting my own company, now I was Usman Muzaffar private eye. And I would use ethereal like a gumshoe detective. I was always on the lookout to try to figure out how something worked or prove someone wrong. You know, got my first cable modem. The send receive lights won't ever stop blinking. Why are they blinking? No one is doing anything. Every laptop is closed, no cell phone is even existing. Why are the send receive lights in my home cable modem blinking? Finally one day I was like, that's it, I'm wiring this, I'm firing up ethereal. Like, oh my god, there's an ARP flood coming. Now you try getting on Comcast support and explaining to them that, yeah, your bandwidth is fine, everything is fine, but I know I'm getting too many ARP requests. That didn't go far. Later, I started connecting, as the SaaS revolution took place in 2010, I'm connecting to all sorts of different companies, Salesforce API, the LinkedIn API, and every now and then things wouldn't work. And again, there was that same instinct of pulling up the packet trace and trying to prove, are you wrong or am I wrong? Who's at fault? Let's get to the bottom of this. Now, I don't use Wireshark. And it occurred to me as I typed that sentence in the slide, like, wow, I'm talking to a room full of Wireshark developers. What if everything I say in the rest of this slide deck is total nonsense? And everyone's going to come up to me after the conference and go, dude, we already do all of those things you thought were the future. So apologies in advance if that's the case. Just nod and smile politely, and later on you can tell me that you already built everything that I think might be interesting to consider in the future. But now, as what Gerald was mentioning, I lead a team at Cloudflare. And Cloudflare is a giant proxy that sits in between the visitors of the internet and millions of website properties. And what do? We make things safer. So bad guys who are trying to take your site down during a conference can't do it. We make them more secure. We make them more reliable. If your origin goes down, we can load balance around it, and in fact, some cases keep serving your site with a cache. And we make things faster, which is what all CDNs do when they've got edge networks around the world. So that's what my team is doing. I'm quite removed from development. I don't have a checkout of sources, not usually anyway. So why is Wireshark still very much on my mind? And in some ways, more on my mind than it's ever been. It's because, to me, Wireshark, that picture, the packets and the color bars and the bytes and the detail below, that's my mental model for wire traffic. That's what I think of. That's what my brain goes to when I think about bits on a wire. And bits on a wire and things moving between our clients and our servers is exactly what Cloudflare does. So in a way, I'm thinking about Cloudflare, I'm thinking about Wireshark more than ever, because I'm constantly asking myself, what would I see if I fired up packet trace, if I was looking at the traffic when this product comes to life, or when this kind of attack happens? Even though I'm not actually bringing it up, my brain is virtually doing that. What my brain is actually doing, and what I'm doing, I spend all my time in conferences and in meetings talking about, are the big three. If you're ever an engineering leader, or you're ever interviewing for an engineering leader, and someone ever asks you, hey, what's important for an engineering leader? There's a stock answer to this. It's, well, there's three things. There's people, process, and technology. And it's a little cliche, but it's very true. Almost all my job comes down to engineers, and managers, and product managers, and salespeople, and how are they interacting with technology. And especially as we get bigger, Cloudflare just broke 800 people. It was only 400 when I started, which was only a couple of years back. How are we building process around to make sure that all those people can build and can do their job? And one of the things that comes to mind to me very quickly is tools. And I mean tools in a very specific sense. Whenever people are trying to do their work, whenever people are engaging with a process flow, or engaging with product, or trying to make a product, or watch a product run, there's a tool involved. That's what software companies do. We build tools to watch what's going on, to help keep track. And Wireshark is a perfect example of a tool that I think fits in that category, the kind of transformative tool that becomes bedrock, that becomes the lingua franca of how people, process, and tech connect. And the questions that are actually in my mind are, what should our tools be doing that they aren't doing today? How are we going to get them to do that? How do we motivate? And tools have a natural evolution. What is it about a tool that makes it start to achieve wherever its destiny is? And then most importantly, how do we think about how tools will affect people, process, and technology? It's all questions about the future. How are we going to think about how tools evolve, what their impact is? Don't have a crystal ball. How can we ask this? And I'm not just meaning this in the Cloudflare sense. I mean this industry sense. What will these tools look like, tools like Wireshark? How will they evolve? How do we sort of get a handle on how they might evolve and what a good evolution for them would be? I think one way you could answer this is to think about how other industries have answered their problems. And to basically cheat. We're a new industry. We've only been around for a handful of decades. I remember being in a talk right here at the Computer History Museum where they said, does anyone know what the first computers were? And of course the answer is, there were people. Literally, that was your job title, computer. So we've gone from that all the way to massive computation, thousands of machines at the edge, which now we call computer. So we're a new field. Let's pick an old field. Let's pick a field that's really already been around for centuries and try to find their equivalents of tools that sat between people, process, and technology, and watch what those tools did. So I picked life sciences. Here's why. Before that resume about coming out here and working for big companies, I was actually studying to be a doctor. And in fact, my whole family is nothing but physicians. Both parents, wife, brother, everybody. I'm the black sheep. I'm the weirdo who doesn't have a stethoscope. And I almost wasn't the black sheep. I was in med school. I got a degree in molecular biology and cell biology. I got as far as halfway through medical school, and I was bored. I just couldn't connect to the content. And at the same time, someone introduced me to this thing called Mosaic, and news groups, and Usenet. And so there's me literally going, yeah, this stuff, pathology and anatomy is cool, but have you guys heard of the internet? Seriously, have you guys heard of the internet? This is going to be amazing. And finally, one of my friends said to me, I think you're in the wrong field, man. And I was like, yeah, I think you're right. So I left med school, much to my parents' disappointment, but I haven't looked back, except on occasions like this. Because if you ask me to think about a different field, it's not hard for me to think about medicine or life sciences in general, because I have this sort of connection to them. And this is it. This is the longest cold open ever for a presentation. This is my thesis, which is, I think Wireshark is to software engineering the same way a microscope is to life sciences. I think that we might learn something if we just spend half an hour, 40 minutes, just Googling a little bit about what microscopes did and how it affected their field, and then trying to replay that in our field and see if there's any parallel that makes any sense. And you might be like, this is a really bizarre idea to even conceive. But if you literally just Google Wireshark and start reading the history of Wireshark from the Wireshark.org website, it says in '97, Gerald needed a tool to track down network problems, and he wanted to learn more about networking. He thought he'd hit both at the same time by building Ethereum. If you do the same thing for microscopes, you learn about this gentleman named Lehman Hoek. I'm probably saying that wrong. Apologies if you know the right pronunciation. 300 years ago, he's in a dress shop with drapery shop where he's concerned with fine fabrics. He's like, I don't think I can really quite see the fabric properly. Wouldn't it be cool if I had a better visibility? I have a concrete problem and endless curiosity. Concrete problem, endless curiosity. Way more curiosity than is necessary to solve the problem at hand. Those are the raw ingredients. That's how it starts. You get those two in the room together at the same time, things like Ethereum show up. Things like Microscope show up. So that's why I think this is an interesting thing to use as an analogy. So that's what I'd like to do for the rest of the talk. I want to pick randomly, semi-randomly, a couple of stories from the history of microscopes, try to look at them, no pun intended, through the lens of software, and see if we learn anything. Can we make any prediction? Could we call a shot? And in particular, let's do it for process technology people and for people I'm substituting education. These specific areas, because it had a profound impact on history. So, I'm not a science historian. I don't know any more than just by Googling around Wikipedia. But I thought, if I'm going to talk about what happened 200-300 years ago, let's just do a crash course in how the microscope worked. So, for a long time, people wanted to look and see things smaller. The closest anybody got was basically building the equivalent of what we would normally think of as a kid's magnifying glass in the 1590s. And then 100 years go by, and two scientists, and they didn't call themselves scientists. In fact, there's a fascinating history. One of them was like, don't call me a scientist, and I've never read my papers in Latin. But they started messing with lenses. And there were sort of two different ways of looking at this. Lehman Hoek just got really good at grinding glass to the point where he could focus light and get a good image. And Hooke started studying everything and drawing pictures of what he saw. He's the one who first saw cells. He's like, oh my god, there's stuff in here. And I just pasted this verbatim from the website where they were talking about history of engineering, history of the microscope, and I'm just going to read the sentence. You saw bacteria, yeast, blood cells, many little tiny animals. They couldn't believe it. But what is all this? Oh my god, in a drop of water. Look at all this stuff swimming around in here. Hold that thought. Look at all this stuff swimming around in here. What else kind of does that remind you of? What is all this? Let's start documenting this. Let's start, word for word, dissecting this. And writing it up and sharing it. And that's the 1600s. And then, long pause. 200 years go by. Almost no change. If you look at the timeline, there's this big gap. It's almost like someone deleted a few new lines from the story. Until the 19th century, these guys are like, you know what, we're tired of seeing the blurry edges. We're tired of seeing the chromatic aberrations, the spherical aberrations. Let's nail this. The reason all those lenses say Carl Zeiss on the side, on the perimeter, Carl Zeiss, the company, and a bunch of really smart scientists nailed all the lens problem, got it down to the point where they could actually get an image that they could prove mathematically, we're not going to get better than this. This is the limit of light. And that microscope, that's a picture, apparently you can still buy these. That's from a shot I got from an auction site of a Zeiss microscope, late 1800s, and it basically looks like the kind of thing we might have used in high school. And then another 50 years go by with no change, and someone has the bright idea, why are we using visible light? Why don't we use electrons? And now you get these stunning 3D micrographs of I think that's an ant's head. And the magnification now, instead of being 2,000, goes to 10 million. We're looking at atoms. It's nuts. So that's it. That's my history of the microscope. And what I want to do then, again, is for each of 3 different stories, how did the microscope affect how people did their work day to day? What might we think about how we might change what we do day to day from our tools? how did it change what was built? Now, life sciences is about discovering and fixing things mostly, but it's also about creating things in the case of drugs. So how did the microscope affect that? And finally, in some ways, most importantly, how did it affect how we taught new generations of scientists how to think about these subjects? And I thought I'd pause for a second, because I'm guessing at least somebody in the audience is calling BS on the whole thesis. Because one is science and one is engineering. And they're not the same. And it reminds me of an old joke of the farmer and the stars. I'll tell you a joke. So the joke is that a bunch of grad students from the local, astronomers from the local university said, there's too much light pollution, you should get out in the fields, stare at the night sky, we'll get a great shot. So they get out on a dark, starry night, and that's Pollux, and they're talking about the distance of the stars, the composition of the stars, their ascension and descension, and what are the materials in, and sitting in the corner just off out of reach is an old farmer who happens to work at the farm, and he was astonished. Oh my God, how could they learn so much about it? It's just a point of light in the sky. And he thought for a second, he said, well, I guess, they've got telescopes now, they can probably gauge content, they've got these things called spectrometers, they can probably measure the kind of radiation that's coming off, and they've got all these tools to measure angles and descent. Gosh, the one thing I can't figure out is, how did they figure out the stars' names? And that's kind of what's going on here. We created the packets. We didn't discover packets in the wild. We're the ones who wrote them down. We can point you to the RC. This is what's supposed to be in byte 4. So in some sense, why are we talking about a diagnostic tool, an investigative tool, when we're the ones who created the universe that we're investigating? And the answer is because the complexity has reached the point where it is a science. And we really are applying the scientific method. And even if you said, well, maybe your code base is so complex, ours, we understand ours, then there's science, and there's ancestry. At this point, so much of Cloudflare's stack is not written by Cloudflare. We sit on top of Nginx, on top of Linux, on top of Golang, we sit on top of the giant, stand on the shoulders of giants, just like they did to advanced software. And then, it really is inherently chaotic. There really are indeterminate conditions. It is non-deterministic, and if it's non-deterministic, and you need to figure out what's going on, humanity has only figured out one tool, and that's called the scientific method. You set up a control, you do some tests, you compare them against what you expect, you pull out a theorem, and you say, what's true? We're always putting bits in the beaker, so to speak. That is what we do as technologists. So I think the analogy is fair. So if we say the analogy is fair, let's go back to my first question. Process. How did microscopes affect the process, the day-to-day process of life science? So the field to think about is called pathology, which is the study of disease. And this gentleman, Rudolf Virchow, German, was the first person to start to use microscopes to say, I don't think we're falling sick because of evil spirits. I think all those things swimming around in that drop of water, I think one of those were making us sick. And he was the first one to start to tell students, use microscopes. Think microscopically. And he's the one who's basically founded, who's considered the father of modern pathology. And when I was in med school, I didn't get as far as pathology. The pathology instructor was the most arrogant SOB of them all. Because he stood up there and goes, all of what you're learning is all just empirical nonsense. At the end of the day, this is medicine. This is the study of what actually causes disease. And the rest of all that is just an approximation, an abbreviation of how to actually change the process that I'm going to tell you in the next lecture is what really underlies heart disease or cancer or stroke. This guy was even called the Pope of medicine because they started to be able to explain this is the biological, this is the scientific basis of disease. And about a century ago, they're like, yeah, this is a field in its own right. This is how we should study disease. And all hospital departments have a pathology department. And in fact, I worked in one. When I was 15 years old, my parents, again, were doctors, were like, well, you're not doing anything useful, you should go sit in our pathology lab. And it was weird and gross, but I did it. And one of the tools I got to learn it's called a microtome. And a microtome is a deli slicer. There's no other way to describe it. You can try to pretend like it's not a deli slicer, but that's exactly what it is. You put a hunk of stuff in it, and you run this thing, and little slices come out. It just costs an arm and a leg because the slices are unbelievably thin, because the whole point of slicing it is to put it under a microscope.
But I don't want to talk about a regular microphone. I want to talk about this awesome gadget called a cryostat. This is cool. You may not know this is how this works. If you are in the operating room and you are trying to figure out what a mass is, they don't know, is this tumorous or is this benign? And what the surgeon is going to do is going to depend a great deal based on a right now Boolean decision in real time during the diagnosis. Is this cancerous or is this not? So they need a decision immediately. So what they do is they take a little bit of tissue and they freeze it. And they basically give it to a cryostat, which is a microtome in a freezer. And in a block of propylene glycol, I think, they freeze it and they slice that. Now it's literally melting, but it's enough now, it's fixed that we can put it under a microscope and look at it. It's not perfect, it's not as good as a real sample, but it's a runtime evaluation. And there's all these studies that go, actually, it's really close enough. It gives great information to the surgeons. So not only does this become standard, they write this down. It's industry standard, the frozen section procedure. This industry figured out this is the way we should do real-time diagnosis when we're in trouble. When we need an answer immediately, there's a protocol for this. There are tools specialized for this. Does this remind you of anything? This reminds me a lot of something. When if I get looped into an incident, it's usually pretty bad. Things happen all the time on the internet, but every now and then something really bad might happen. And we have the exact same problem that we were talking about all morning, which is we've got to figure out fast what's going on and what might be at fault. And I'm watching Incident Channel or a Jira ticket where things are, and all the right decisions are being made. We definitely have track and trace. What cola should we think it should be in? I think it better be out of the San Jose cola. Does anyone have an idea of traffic? Yeah, I think let's get some traffic in here. Who's got the thing? Let's page SRE, let's get them in. If we get the packet trace, do we know who's going to look at it? Yeah, I think that guy from the cache team will be able to look at it in the morning. And there's this long ad hoc conversation about all this, and a pcap file is going to get attached somewhere, and someone's going to bring up Ethereal and study it. The problem I want to posit is, our tools have no idea that we're doing this. Wireshark and pcap and all those things, they don't know the way a cryostat knows that they are emergency runtime tools. And I think we might ask ourselves, how might tools evolve? What will be our cryostat? What will be the package capture for emergencies? What features of Wireshark can we get out of the way? Can we model the experiment? So often it comes down to, I know what experiment I want to run. Someone needs to make this request, I need to capture it. Someone needs to make a different control time request, I need something to diff it. And then based on that, if I see this kind of difference, I want the following test, and if not, then I want the following different. Why can't that be streamlined? Why can't we get the tool to guide this discussion? I think this is an interesting avenue of approach. And more interestingly, I think our industry needs the moral equivalent of a frozen section procedure. The same way the life scientists and the doctors were like, and remember, they were dealing with way more variables than we are. But they still got a basic process down, and it's worldwide, and people count on it, and it works. And it took them centuries to get it right. But I think something analogous to that would be useful for us. Let's switch to a different topic. So, what about how microscopes change the way we design stuff? So pharmacology is the study of drug discovery. How do we make drugs and do things? And for a long time, this was purely empirical. They would chop out a little bit of frog tissue and they'd put it in a bath of saline and they'd inject something and they'd throw current through it and see if it still twitched. It's like painting with boxing gloves on, right? It's like very, very crude. Until in the late 19th century, another German parliament started to say, I think we could target medicine to the thing that is causing the problem. And this is the first time that people start to think that, wait a minute, what if there's actually something specific wrong, and if we could just nail that, we could fix a problem with much greater accuracy. And this is the broad theme here is, if you know what you're looking for, then you can target that thing. And so it took a century, but eventually, this is what's called rational or drug-based design, which is, let's take a picture of the target. X-ray crystallography is where you shoot an X-ray beam through it, NMR is where you irradiate it. Now there's different kinds of fluoroscopy. But at the end of the day, it's all, if you could show me a picture of the thing that's causing the problem, then maybe I could engineer something to jam it. And if you get it right, it will fix only that problem. And the basic problem with chemotherapy for the longest time was that, yeah, it killed the cancer cells, but it also killed a lot of the good cells. People would get very sick. If anybody knows anyone who has the disease called chronic myeloid leukemia, when I was in med school, we were told it's a very grim prognosis. It's got weeks to months. And I actually know somebody who has this. And this drug was designed entirely by that. This was a drug called Gleevec, where they basically nailed, we can create a small chemical that will knock out the problematic molecule. And Gleevec has basically cured this kind of cancer. The people are now surviving at 17 years, and they're doing fine. So the impact here is extraordinary. And it goes from the microscope, and of course this is not an optical microscope, we're using the term microscope in the broader sense, to not just asking your tool what did happen, but rather asking your tool what could happen. And you know, and this is still going on. This is a picture of the Zika virus, and these guys won the Nobel Prize last year for a better way of identifying what its structure is. So again, how does that relate back to us, back at the terminal? What do we take away from that? If you think about what Cloudflare does, like I said, we're sitting in the middle of traffic and we want to do useful things. And one of the things we might do, we want to block traffic or put up a CAPTCHA or rate limit it or redirect it. There's all sorts of things we want to do. And in an ideal world, I give my customers that facility. I give them a programming language that says, here's your if statement. Write an expression that matches the traffic you care about, and then write a little pseudocode. This is not real. This is me just spitballing in a virtual language. But the question our engineers quickly came to is, how are we going to describe that filter? How will we describe to the customer what traffic they're interested in? What do you think they reached for? The tool that they normally use when they describe traffic. You know what would be great? If it looked like a Wireshark filter. That's tools informing design. Now we're going in the other direction, right? So now the Wireshark filter language that the team has cooked up is affecting the mental model of how engineers think about how do you filter traffic. Cloudflare's working on this. It's not ready yet, but we want to get to a point where you can type the moral equivalent of a display filter expression and then use that to describe the traffic. Because that's how we would want to do it. That is how we do it, after all, ex post facto. Again, it's this move from what did happen to what could happen. So, zooming out all the way, the guys who were looking at, ant heads, and this is a core 300 years ago, they never imagined that we would be able to get the 3D structure of the Zika virus and try to target it at that level. So in the same way, just go nuts, think science fiction level. What does the Wireshark of the future let us introspect? This information is flowing over wires all the time. And if you had the Wireshark trace of what the CPU was doing to RAM, or how it was going with I/O, if you had God's eye visibility of every bit, every 0 and 1 that ever moved over anything, what would you want to see? What might that change of how you wrote fundamental components or rewrite them? Because now you have a better idea of their receptor. You have a better idea of what environment they execute in and what behavior they should change. That's, again, a vague idea of how I think tools can evolve. When tools give us a clear enough picture of the world in which we're operating, it changes in our decisions of what we think could happen, not just what did happen. And the third topic and final topic I want to bring up is education. So, all of us probably took high school biology, and you probably had to stare in a microscope. Again, I was in med school for a year or two, and so I had to take a class called histology. Histology is brutal. There's hundreds of slides on the desk, and you have to take each one and you stare at it. And the way you're tested on histology is, there's literally a room that looks like this one with 100 microscopes, and you have a timer, and you go ding, and you look at the thing, and you have to write down what you see, and then you go to the next station and you write down what you see. I don't know why they didn't use slides. It seems like a bit easier. But the histology professor had a very interesting thing that always stuck with me. He said, my goal is for you to be able to identify the class of tissue in 1 second. In the same way that if I gave you a freeze frame of a sporting event, you would be able to say in 1 second what sport that is. If I just flashed a shot from ESPN, you'd be able to tell me, yeah, that was basketball. Or no, that was soccer. Now, if you're really good, you might be able to say, yeah, that was basketball, that was the Bulls. right? Or that was a match from FIFA. Or you might be able to click out specific players. But what if we're just talking about, with a 1-second glimpse, can I identify what sport this is? But that's muscle. And notice, this is microscopes being introduced. No one's troubleshooting anything. No one has ever put this up or brought this up in the context of a problem. It's simply, look at this, this is how the world works today. And you should have a feel for how the world works today. Look at that thing. That's a 10-way microscope, so that 10 different students can see the same thing at the same time. And you might think, well, why can't they have visual microscopes? They do, which we can project. But part of it is the hardware, literally how you prepare the specimen and what other dyes you can use, and having people physically look for microscopes, since that's what they're going to have to do when they're in the field. This is the kind of tools that industry evolved because they took education seriously. They actually had to build a $25,000 microscope that lets 10 people look at the same thing at the same time. So, I was preparing this talk. I mentioned that 30 years ago I was a 15-year-old in a path lab. Well, now I have a 15-year-old, and he just finished 10th grade, and he took computer science in his class. And I said, come over here, sit down, I want to show you something. And I fired up Wireshark, and his first sentence was, wow, what is all this stuff? That same visceral feeling we all had the first time you discover how much traffic is on your home network and how many weird protocols are going back and forth over the net. And his eyes just opened up like, I didn't have any idea that all this was going on. And we're shutting down apps so that the trace quiets down and we can start to focus on things. Finally, I said, what's your favorite video game? Fire up League of Legends. And I know League of Legends is a Riot Games property, and I know Riot Games is a Cloudflare customer. Of course I know that. Of course I know that. But I see the DNS packet trace and see the name redirect to Cloudflare.net. I was like, look! See? That's DNS getting involved. And he's like, oh yeah, you mentioned that. And then synax. And I was probably the nerdiest dad of all time. I was like, just wait here, wait. And I bolted downstairs and I pulled up Stevens and I flipped to the table with a three-way handshake and I said, now read this table and see if you can correlate it with these three lines. And of course, now you can. When you see the table, Stevens' description of the TCP handshake, and someone is showing you the three lines at the same time, it makes sense. I see it. I just logged into riotgames.com. Yeah, I get it. That's the beginning of the conversation, just like it says in the book. But I guarantee you, if Wireshark was not up, and I just showed him that, again, it's all abstract. It's not concrete. Then we picked a different game, Agard.io, which is a really popular web-based game. And all this WebSocket traffic shows up. Never heard of WebSockets. It's a WebSocket. Let's go learn about that. And my kid said to me, yeah, they never really taught us this. They never really showed us anything with zeros and ones. That's the way he thought of it. He saw zeros and ones. And he didn't have the words for it, but he wanted to say, someone's got to show me a sector editor. I don't really understand what's on a hard drive. Someone's got to show me a process analyzer, something where I can inspect what RAM looks like. He didn't have the words for this, but that's what he's getting. Someone needs to show me strace so I can see what the user space kernel boundary looks like. This is when things become clear. For those of us who remember using these tools, that's when the light bulb goes off. I claim that what we should start to do is think about Wireshark in the beginner's kit, or a version of Wireshark that is tailored for beginners, that maybe simplifies it, so that we can start to challenge our students with the same thing. In a 1-second glimpse, can you tell me what protocol that is? Does that look like HTTP to you? Does that look like a Dropbox LAN sync request? And I think that's another avenue for where our tools could evolve, to think about they are responsible for creating mental models. 30 years later, I'm still imagining the Wireshark UI when I think of traffic going across the team that 200 people are working on. So, how do I think of how Wireshark might affect our future? I think that it could affect our process by being more aware of the context in which we use it. I think it can affect our technology and what we decide to build by giving us better context for the environment in which we're building. And I think it can dramatically affect our education by making it real, by giving students an actual understanding. These are the zeros and ones going over the wire. Software has a killer feature, and I think the world has the wrong bullet when they think about software's killer features. Most people would say the awesome thing about software is that you can change it. Yeah, that's true, but it has an even more important killer feature. all of those tools, those guys were not biologists back in the 1700s. And the ones later, people like my parents and my family who are doctors, they are not microscope engineers. They are not physicists who know how electron microscopes work. And pretty much any other field, carpenters don't make hammers, right? Astronomers don't make telescopes. Doctors don't make stethoscopes. Software engineers write compilers. We are our own toolsmiths. We have an enormous advantage over all the other disciplines. We can build our own stuff. We're not beholden to another discipline to have a breakthrough that might be centuries away before we can implement ideas that come to us. This is the best part about software, is that our tools are in constant evolution because we are the ones who are using our tools and we're the ones who's creating it. That's the real turtles all the way down truth about software. And with this advantage then, I think we can think about Wireshark that information is always going to be flowing over wires. I was talking to a friend, like, airplane mode is over. Almost all flights have Wi-Fi now, and I've read somewhere that they're thinking of removing the screens because everyone brings their own device. So the world in which we think of an isolated computing instance is gone, and even inside one of our computers today, there's so much traffic going over wires. So there will always be a need to introspect, to monitor, to categorize, to analyze the data as it moves across those wires. And I think we should do that not just because we need to troubleshoot it, but because it actually makes us better engineers, better technologists, and better teachers. And that's it. Thank you very much.